Welcome to an edition of CCSD Living Environment. Today we're going to talk about graphing. A graph is a visual representation of numerical data that's been collected during an experiment. You're familiar from the past with pie charts and bar graphs and line graphs. We're going to spend most of our time this year with line graphs, but before we start getting into the parts and pieces you need to have, I want to first review a couple others. The first one we're going to talk about is a histogram. A histogram is used to display how a certain variable is distributed, and they're usually done without a gap between the bars. The bars are actually touching. And the values are done in ranges, like 51 to 60, 61 to 70. So the histogram, it's not a specific value. It's giving you a range of information, and your bars actually touch when you're all done. As opposed to a bar graph that displays data in separate columns, where the height of the bar actually indicates its value, and the bars do not touch. So there's a space between each bar. We'll spend a little bit of time, we'll do a couple of these, not many throughout the year. Most of our time, most of our effort will be done with a line graph. A line graph is used for analyzing trends in a specific variable by plotting continuous data by points and then connecting the points with a line. The most important thing for you to remember about a line graph is to connect the dots. People will go through, they'll put down all these dots in exactly the right place, but then they never connect the dots with the line. To complete your line graph, you have to draw the line. What are the parts to the line graph? What are the things that every time you do a line graph, you have to remember to have? The first one is the title, a concise statement to tell us what the graph is about. Doesn't need to be long, it can be short, but it needs to be as specific as possible and tell us what is this graph about. What are the variables that you're graphing? And a key, a short description of the graph's data. What we're going to use are what they call point protectors. So if I'm graphing the difference between boys and girls, in all of my boys' data points, I'm going to put a triangle around the point. For all of my girls' data points, I'm going to put a circle around the point. Still connect the dots, but I can quickly look and see which ones are boys, which ones are girls. And the important thing is, if you made a mistake, you just have to fix that point. If you use a crayon or a pen to draw your lines in different colors, then you have to redo the entire graph. You can't just erase one point because we can't erase those things. So by using point protectors, cold and hot water, square for cold, diamond for hot, you can quickly see the difference between them, and if there is an error, you can just erase it to fix it. You don't have to redo your entire graph. Doesn't make any difference which shape you use, as long as you have a key to designate what your data points are. The independent variable. The independent variable is the variable that's being tested, or it's the factor that the scientist purposely controls. If I have a beaker of water on a hot plate and I want to take the temperature of that water every minute, what is my independent variable? I can control the time. I can set my stopwatch so that every minute I take the temperature. I have no control over the actual temperature of that water. So my independent variable is time, because it's the variable that I actually have some control over. We're going to put that on the x-axis or the horizontal line. The dependent variable is what you're measuring. It's the result of what happened during the experiment. It's the data. It's the result. In the example I gave you, it's the temperature. That's what I'm measuring. That value is going to go on the y-axis or the vertical line. So if you look at the axes I sketched out, x-axis is on the horizontal line, y-axis is on the vertical line. Independent variable goes on the x-axis, dependent variable goes on the y-axis. I want to talk quickly for a minute about those two axes and about that point in the middle, about this point right here where the two sides come together. That's referred to as the origin. and you have to make sure that you label the origin for both sides. So I could start here at 0 and go up. I could start here at 0 and go up. I've labeled the origin clearly on both sides, and it started right at that point. Or I could start here at 5 and go up. I could start here at 0 and go up. Again, I've clearly labeled the origin on both sides. Notice it does not have to be 0. You can start anywhere on the number line. All you're doing is pulling a section of the number line out and putting it on the scale for your graph. You can start any place you choose as long as you label that origin. That's all that you have to do is label the origin. If your origin is 0, 0, if it does happen to be 0, 0, you need a 0 on the x-axis, you need a 0 on the y-axis. 1 0 written diagonally in the corner isn't going to cut it. Take the 3 seconds it will take you and put the 0 on both sides. So when we talk about those axes, we know that we put numbers on the axes. Those numbers are called the scale. So let's talk about the scale that we're going to put on each axis. First of all, we need to make sure that all of the data points are included in the scale. We need to make sure that we label the origin for each axis, which we just talked about. It needs to be something that's easy to manage. It's easy to count by 1 or 2 or 5 or 10. It gets tricky when you try to count by 3 or 12 or 65. They're strange numbers that we're not used to using. Try to stick with a number that's easy to manage, that you can count by very easily. Each block should have a consistent increment on the axes. In other words, if I go 1 block on my graph and that 1 block is equal to 5, then 2 blocks is equal to 10, 3 blocks is equal to 15, 4 blocks is equal to 20. Or if 1 block was equal to 10, then 2 blocks is equal to 20, 3 blocks is equal to 30, 4 blocks is equal to 40. Doesn't make any difference what number you go by as long as each block is equal to the same increment every time. Do not break your scale with one of those little squiggly things. Your graph does not have to start at 0. But the origin does need to be clearly labeled, and if you put a squiggly in there, you're not going by something consistent, and you don't have a clearly labeled origin. So start with whatever number you want and go up from there. But don't put that little squiggly guy in. Your graph needs to take up as much space as possible. So if your first data point is 2000 and you have to go to 2020, 2000, 2001, 2002, 2003, 2004, 2005, easy to manage. I'm going up by 1. Consistent increment, it's 1 each block. And I'm going to take up as much of that graph as possible because I'm going to need to take up 20 spaces on there. So it spreads out the data. It makes the picture more easy to look at. So let's look at the sample that I've given you. I have a title, the effect of time on temperature. I have a label with units for my x-axis. I have a label with units for my y-axis. I have a scale. It's a consistent amount. It's easy to go by. I have a scale here, consistent amount, easy to go by. I plotted all of my points. I connected my points with a line. And I have a point protector around each point. When you look at the data table, something I want you to notice is the left-hand column of your data table is your independent variable. That's what goes on the x-axis. The right-hand column of your data table is your dependent variable. That's what goes on the y-axis. So I went through and plotted all of my values. Now notice that 20 was my first temperature reading. So I started at 10. 52 was my last temperature reading. So could I stop my scale at 50? No, because the first thing says I have to include all of my data points. 52 is a data point, which means I had to put 60 on there so that 52 was included in my scale. Something to be very careful about when you get to the top side of your scale. Make sure that the last number you end on has included the highest value you have. Can I just stop at 5? Sure, 5 is my last point. But I can't stop at 50 because 52 is my last data point. So that just gives you an example of all the parts and pieces that you need to make sure that you have. My origin is very clearly labeled for both axes as well. What else do I need to have? I need to have a valid conclusion about the graph. I need to state the relationship between the x and the y axis. Remember, if it asks you about the relationship, it's asking you, did it increase? Did it decrease? Did it remain the same? That's what it wants to know about the relationship. So on what I just showed you, as time increases, the temperature increased. So time was my x-axis, it increased. Temperature is my y-axis, it increased. So as time increases, temperature increases. That's all you need to do when you state a conclusion about the graph. You're telling me about the two variables that you just had in your graph. The last thing we need to talk about when it comes to graphing is estimating values that were not in the data table. And there's two different methods that we can use. The first one is called to interpolate. It's the value that's between two of the measured points. So on the bottom I had from 0 to 5. If I wanted to know what was the temperature at 2.5, I'd go halfway between 2 and 3 on the x-axis, I'd follow up to the line, and I'd go over. Let me show you. So if I wanted to know what would it be at 2.5, I'm going to go from 2.5 up to where the line is that I graphed, and I'm going to go over to my y-axis. It's inside two of my known values, so that's called to interpolate. It's inside. And the next one is called to extrapolate. Extra meaning outside. So it would be if I asked you, what would it be at times 6? Well, at times 6, I could continue the slope of this line. 6 would be here. I'm going to come up to where they meet and go over. It's an estimation. It's not an exact value, but it gives you an idea for where things would be at that point. So to extrapolate, it's a value determined outside the known plotted values. We're going to extend the line along the same slope. We're going to follow that same slope and figure out, okay, what would that value be? So interpolate is if it's inside, extrapolate is when it's outside the values from your data table. So let's look at this axis that I drew for you. Again, x-axis is the horizontal line, y-axis is the vertical line. So how can we remember what goes where? Well, we can talk about die, right? What do we have? Dependent variable goes on the y-axis. Independent variable goes on the x-axis. What else are we going to do inside here? We're going to interpolate. And then what are we going to do outside here? We're going to extrapolate. So dependent, independent, interpolate, extrapolate. Hopefully that helps you a little bit to remember what goes where and how you know if it's dependent or independent, and which one is inside, interpolate, and which one is outside, extrapolate. I hope that helps a little bit with line graphs, and I'll see you next time.